So today we're going to go over kind of two different topics. We're going to go over solubility, which is probably going to be mostly review for you guys, and we're going to go over the polar nature of water. We're going to talk about how a water molecule works and why that makes water do so many weird things, okay? But also why it's so crucially important for life, okay? Okay, polar molecule. So this is new. We talked about the other day like ionic bonds, and we talked about covalent bonds. Okay, the ionic bonds were super weak because the electrons just get traded, okay, from metal to non-metal. But the covalent bonds were super strong because those elements had to stay together because they had to share that electron. Okay, there was no other way around it, and those bonds were really, really strong because of that sharing. That makes it sound like the sharing is really nice, but in a lot of cases, I shouldn't say a lot, in some cases, the sharing is more like sharing in air quotes, okay? Like one gets to share it a lot more than the other does. That's what makes a polar molecule, okay? Is an unequal sharing of the electrons. Water is a prime example of a compound where one element gets the electrons a lot more than the other. Okay, it's like you go, you and your friend buy a pizza together, and the sharing consists of they get 6 pieces and you get 2. Okay, that's kind of what a polar molecule is like when we're talking about sharing the electrons. Okay, they spend a lot more time around one than the other, and we'll talk about why that happens. Okay, so solubility. Okay. The definition of solubility is the degree to which something will dissolve in something else. A solute will dissolve in a solvent. Okay, and that'll actually be up on the board here in a minute, guys, so don't worry about trying to write what I said. It'll be up on the board in a sec. Okay, so not everything has the same solubility. We saw that yesterday in the lab because one of our tests was solubility, and we saw that not everything dissolved in quite the same way. Okay. Now, generally, when we discuss solubility, we're talking about of something in water. Is water the only thing that will dissolve stuff? No. Okay? Like if you put on nail polish, okay, can you wash that off with soap and water? I'm assuming you can't. I don't wear nail polish, but I'm assuming you can't wash that off with soap and water. Okay? You generally have to buy nail polish remover, okay, which contains acetone. Well, acetone can dissolve nail polish, okay? But nail polish won't dissolve in water. It's not soluble in water, okay? Similarly, if you're using oil-based stain or paint and you get that on your skin, that is not coming off with soap and water. It's made of oil, okay? And oil doesn't dissolve in water. So you generally have to use paint thinner. Nail polish remover will generally work for that as well, okay? Or, not that I would recommend these substances for removing paint from your hands, gasoline or diesel fuel, okay? Because of, the flammability thing with those, okay? I would recommend getting those all over you. But they'll take it off because oil is soluble in other petroleum products, but not in water. Making sense? Okay, so solubility, the definition is how much of one thing will dissolve in something else. Water's the most common one, but it isn't in the definition. Okay. Now, a substance is said to be insoluble if it will not dissolve in another substance. So that term, insoluble, that's important. Insoluble means won't dissolve. Sometimes in a chemical reaction, okay, when the elements are being rearranged, as Dalton said in his theory, okay, when they get rearranged, sometimes when they go back together, they create obviously something with different physical properties. But sometimes one of those physical properties is that they're no longer soluble, and we'll see a solid actually form as a result of the reaction. Okay? And what will happen with that solid is it will kind of fall out of the solution. In this case here, we can see that there's this cloudy material here at the top. Okay, that's a solid. It's a fine solid, but it will slowly fall out of the solution and collect on the bottom, which is what precipitate means. And precipitate means to fall out of something else. All right, so precipitation falls out of the sky. Precipitates are insoluble chemicals that fall out of solution. Okay, so the term precipitate is actually both a verb and a noun. I think I got that right. I know teach English, okay, but yeah, okay, it's something like that. I think it's a verb and a noun. Okay, so that actually means to come out or to be something that's not soluble. Okay. All right. Making sense there? Okay. The definition of precipitate is going to come up again in here, so don't worry if you're trying to write down what I said. Okay. If it's insoluble, it will be a precipitate. All right. Terminology here. Okay. This is probably familiar to you. Okay. A solution, and I would write this down. Okay. A solution is any mixture containing a solute, the thing getting dissolved, dissolved in a solvent, the thing doing the dissolving. Water is usually the solvent. Okay? Sometimes even it's called the universal solvent. Okay? If we have a solution that is the thing completely dissolved, then we also call it a homogeneous mixture, or homogeneous, however you want to say it. Okay, so the term homogeneous means like one part or the same. Okay, the prefix homo means one. Okay, so if something is homogeneous, there's one part. Okay, I don't see two parts. Even though there may be two parts, I don't see them. It's something completely dissolved in something else. Okay, where do you often see the word homogenized? Where's a place where you see that word a lot? This stuff is homogenized. Milk, yeah, dairy products. Right? There's an old expression that goes, the cream rises to the top, okay? Because when you used to actually milk a cow to get milk, I mean, not that they don't still do that, but like if you were a person who did that, if you left it in the pail, it would separate. The cream, which would be lighter, would come to the top because it was mostly fats, okay? And the water-based stuff would sink to the bottom. Obviously, we don't want our milk to do that in the fridge, so it is pasteurized, and the process of pasteurization causes it to homogenize, that is, stay as one visible part. Okay? Otherwise, it would separate. Making sense? Lots of things are done that way. Peanut butter, unless you buy like the all-natural peanut butter. Okay, if you've ever bought that, you know right away as you open the lid and there's a layer of oil on top. Okay, most peanut butter is also homogenized so that it all stays as one visible part and the oil doesn't come out. Okay, so if something is homogeneous, it's one visible part. Okay, that would indicate something completely soluble. All right, the other side of that coin is the heterogeneous mixture. Hetero meaning many. Okay, so this would have many parts, okay, or many natures. Right? Two substances mixed together that do not dissolve. We also sometimes can call that a mechanical mixture, okay? Especially if you can suspend one of them in the other by like stirring or something. So yeah, also write down the heterogeneous part here. Okay, so oil and water would be a heterogeneous mechanical mixture. Now, differences between the two. Obviously how they look. Okay, one has only one visible part, the other has many visible parts. But another difference is we know both of them contain two things. How you can separate them is also different. Okay? If I've got this mixture here, I can clearly see that there's this part that didn't dissolve. Could I get that part out pretty easy? Like if I poured it through a filter, right? Would that catch most of it, a paper filter? Yeah. Okay. I could easily separate those by a mechanical means. The other example there was iron filings in sand, so little bits of metal, okay, in a bucket of sand. I could easily separate those by putting a magnet in there and stirring it around, and I'd have all the magnet bits or all the iron bits on the magnet. Okay? I can separate those by a mechanical means. How can I separate what's dissolved in this water from the water? Boil it, yeah. Okay? If I boil this off, I'm using one of their physical properties to separate them. That's being separated by a physical means. I could also separate them by a chemical means. I could make a chemical reaction. And if I make a chemical reaction that will react with whatever's dissolved in there, it might make a precipitate and I'll be able to get it back out. Incidentally, that's how we treat drinking water. Okay? If we don't want things like lead and tin and stuff like that that are heavy metals that are bad for us in our drinking water, because they're in there, what we do is we add chlorine. Chlorine very easily bonds to those materials, but is not soluble in water with them. Okay? So as soon as we add chlorine, not only does it help kill like nasty bacteria and other things, but it will bond to heavy metals and create precipitates that then fall out of solution. Okay? But the only way to get this out is either a physical or a chemical means, whereas for this, I could separate them mechanically. Okay? That's why it's called a mechanical mixture. Okay? Has anyone ever accidentally done this, like boiled off an entire pot of water, you put it on the stove and forgot about it? Okay, and it makes an awful mess, okay? Like, because all the minerals that were in that tap water get left behind, and then they burn onto the pan. And they're really, really hard to get off at that point. But they were in the water, they weren't visible, they were completely dissolved. Okay? But using the boiling point of water, one of its physical properties, enabled us to separate the two. All right, questions on those two terms? The water treatment example is a pretty common application question kind of a thing because it incorporates solubility. After we've talked about reactions, we'll talk about it again because it involves a type of chemical reaction that makes precipitates. It involves the term precipitate. Okay, all of that stuff, it's a good application kind of question for a quiz or a test later on in the unit. Okay, other terminology. So write these two down, solute and solvent. I'll give you a minute to write those two down and then we'll talk about them. Okay, so solute is the thing being dissolved. Okay, whatever it is we're trying to dissolve. Okay, if I put a teaspoon of salt into a big glass of water, the salt would be the solute, the water would be the solvent. Okay, it's why a lot of our cleaning agents, okay, like Pine Sol or Mr. Clean or CLR or any of those kind of things, okay, they're often referred to as cleaning solvents. They basically make it possible for some things that don't dissolve very easily in water to be dissolved, okay, and then taken off, like hard water scales and soap scum and things like that are hard to get off of your shower or your sink. Okay? These things will dissolve them more quickly than water does. Sort of make sense there? Okay? In the same way that when we talk about nail polish remover, okay, the nail polish would be the solute, and the acetone, the nail polish remover, would be the solvent. It's the thing that's doing the dissolving. Okay? That's probably you probably knew those terms from science. Okay. Anybody need that slide anymore? Okay, now, precipitate. This definition is what I was telling you, this one you want to copy down. A precipitate is any solid produced in a reaction that will not dissolve. In other words, it will precipitate out. Okay, give you a minute to actually copy both of these terms down here. Okay, solubility definition, precipitate definition. Okay, so talking about a precipitate here. Next week on the, no, sorry, not next week, Monday the 22nd, we're going to do our lab on chemical reactions. Two of the reactions that we do in that are going to produce precipitates. So you'll take two clear substances, two solutions that are homogeneous. You'll mix them together, and all of a sudden, you're just going to get this solid. I don't mean like a chunk. It's not going to go clunk, okay, down on there, but it'll, like, you'll see this powder form that wasn't there, okay, and it'll precipitate out and fall to the bottom of your watch glass. Okay? You'll see kind of that happen. I'm going to show you a little video here of what it looks like when a precipitate forms from a reaction. Okay? Now, I am going to kind of preface this with, it is not a life-changing video in any way, shape, or form. It's actually quite boring. Okay? The weird thing about it was their choice of music. it's a person mixing beakers together, but there's this very melancholic Italian guitar music playing in the background. It makes me sad when I watch it, because it seems really like a weird match of genres there. Okay, so just if you feel sad, it's because of the music. Okay. Oh, I gotta pause it. All right, and then when we're talking about the term solubility, the degree to which a substance will dissolve in something else, so a solute in a solvent. Okay, how much solute can go into solution before it becomes saturated is based on solubility. Okay, so if you're making, like back in the day, we used to make Kool-Aid by putting like the Kool-Aid crystals in, and then you would add sugar to make it, sweet, or if you make like Tang or any of those powdered drink mixes. Okay, there comes a point where you can't make any more dissolve. You keep adding it, right, and it'll just start to collect on the bottom. Okay, if you want to make it the sweetest it can possibly be, use hot water when you first make it. You can't drink it right away, okay, but you'll get more of it to dissolve. Okay? Then you put it in the fridge, and you'll see it start to collect on the bottom. Now you know that that solution is saturated. It can't hold any more of the sweet stuff that you put in. Okay? It could when it was hot, but it can't when it's cold. So now you know that when it's cold, it is as sweet as you can possibly make it, because no more will dissolve. In fact, some of it fell out or precipitated out because it was completely saturated. Okay? The term saturated literally means to hold no more. So if you go out in the rain and come in like, oh, I'm saturated, you literally are. Your clothes can't hold any more water. Okay? You're literally dripping. Okay? That's where that term comes from. Okay, now, obviously, some things are more soluble than others. We saw that in our lab. And some things should be soluble and others shouldn't. Like the Twinkie. The modern Twinkie is effectively soluble in water. You can put it in a glass, try it. You can put it in a glass, and after a couple of hours, it will be pretty much dissolved. I'm not saying it's going to be smooth or anything, but if you had a broken jaw and you had your jaw wired shut, you'd still be able to eat Twinkies. You just put it in a glass of water and you could drink it through a straw. Okay? Or like that commercial for KD that was on like a year or so ago, where they put it in the blender and the guy, wow, I don't like KD at the best of time, but to think of drinking it through a straw. Okay? But you could do that with a Twinkie. Okay? Does that seem wrong?
Yeah.
Isn't a Twinkie supposed to be cake? Okay, what goes into a cake? What?
Like
Flour, eggs,
baking powder,
baking powder, sugar,
sometimes oil.
sometimes oil. Okay, are some of those things milk maybe, right? Like are some of those things not soluble in water? Eggs aren't. Oil's definitely not. Flour kind of does weird things and clumps up. Okay, but a Twinkie's supposed to be cake. Okay, well, the modern Twinkie is not what the original Twinkie was. Okay, back in like the 20s, okay, when Twinkies first came out, they were cake. They were made from eggs and milk and cream and oils and flour and all that, and the filling was actual cream. Okay, it was banana cream, believe it or not, the original Twinkie. Okay, but it was made with cream, which obviously doesn't dissolve in water. Right? It rises to the top. Problem with those, they had a very short shelf life. Right? By the time you get these Twinkies made and packaged and sent to the vendor, they were already close to spoiling. That's not good if you're trying to make money. So they started modifying some of the ingredients. Okay? During World War II, they had to change the filling because there weren't the availability, the supply chain for bananas had kind of changed and they weren't as available. Okay? So they actually switched to a strawberry filling, which people didn't like, and then to the vanilla filling that we have in them now. Okay? But supply chains and things like that were affected. Dairy wasn't as available, okay? Eggs not as available, and they wanted to increase the shelf life. So they replaced them. Eggs were replaced with a protein albumin mixture, okay? Which changed what property of the Twinkie? Well, not just its solubility, but where does the yellow color come from? Egg. You take the egg out, and now your Twinkie looks like it's made out of drywall. Okay, it's gray. not very appetizing when it's sitting on the shelf. Okay? So they had to add in other things, like yellow dye number 5. Okay? Yellow dye number 5 is a known carcinogen. You can't even use it in food in a lot of parts of the world. Okay? Carcinogen means it causes cancer. Okay? So yeah, it's not good. Now, I'm not saying one Twinkie is going to kill you. Okay? Obviously, everything in moderation. You're having 10 Twinkies a day, you've got real problems. Okay? First off, you've got some real nutritional problems. And secondly, that's a lot of yellow dye number 5. Modified milk ingredients, okay? Non-hydrogenated vegetable oil, high fructose corn syrup, okay? All these other things that are all soluble in water, including the filling, which no longer has any real cream. It has modified milk ingredients, okay? Because all of these things can be mass-produced, put together, and will last forever. After a zombie apocalypse, you could still raid the 7-Eleven years later, and the Twinkie will still be okay. Okay? They could maybe outlive you even, which is kind of scary. That means there's a lot of preservatives in them. One of the preservatives is the same stuff that's in mortician's fluid. Yeah, the stuff they inject into a corpse so that it doesn't smell before the funeral. Yeah, that same stuff keeps things from decomposing. Works really good to keep your food from getting moldy. It's probably also not all that good for you, but it's in there. Hey, yeah, no, I am not. I would be a hypocrite if I'm like giving you a nutrition lecture here because I'm like the worst for like eating unhealthy things. But these are all things that make a Twinkie now vastly different and soluble in water versus its original form, which was not. Okay, there you go. A little interesting sidetrack on that one. Okay, I need everyone to take out their periodic table and flip it over. You will find a chart that looks like this on the back. Give me a sec there. Okay, so if you tried the practice quizzes the other day and you're like, oh, I don't know how to figure out whether this thing is soluble or not, now you're about to learn how to do that. This chart allows you to determine whether a substance is soluble in water or not. Okay, it's really easy to use. Okay, we're just going to go over that right now. So the way it's set up is you've got your ions, usually the negatively charged ones, along the top. And then you have 2 rows beneath that. Okay? The middle row is the row where things are soluble. And the bottom row is the row of things that are not. Okay? So if I was to give you, let's say, this compound. Oh, sorry. No, I got to pick something that's on there. SO4. Okay. If I was to give you that compound, sodium sulfate, what I would do is look for the negatively charged part of that. Sulfate is right here. Okay? Now I need to find out if, when it's with sodium, is it soluble in water? So what I do is I try and find sodium in either the middle row, where it would be soluble, or in the bottom row, which would indicate it's not soluble. Okay? The middle row has the word most in it. Thanks. That's helpful. Okay? Most could mean a lot. It does. So what I have to do is actually have to look down in the non-soluble row and see if sodium is there. Okay? Calcium, strontium, barium, silver, mercury, lead 2+, radium 2+. I don't see sodium in that row, do you? So would that mean sodium is part of most? Okay. Is this stuff soluble or not? Yes. Yes. This is soluble because sodium is here in the very soluble row. Okay, let's try another one. Let's try okay, silver chloride. So I go, this is the negatively charged part, the chlorine. So I go to here, here's chlorine. Says it's soluble with most things, not helpful. Okay, and I see that the stuff it's not soluble with is copper, silver. Soluble or not? Not soluble. Okay, silver is in the not soluble row. Okay, so this would be not soluble. This would be soluble. Okay, what about if I have this one? Potassium hydroxide. Okay. Same thing. Here's hydroxide. It says here, group 1 ions. Where's group 1? First row, or first column. Yeah, first column. This is group 1. Is potassium in that row?
Yeah.
Is that soluble? Okay, so you're going to see that. Sometimes it'll say group 1 and 2, okay, or just group 1. Group 1 means here. If there's anything in there, okay, it's just trying to save space. That's why it uses most in group 1 and things like that. It's just trying to save space. If it listed everything that was soluble with it, it would take up a lot more room. Okay, that making sense? How that works? Okay, try the 8 examples I have there. Okay, just write S or NS beside them. I'll give you a few minutes. We'll do the first 2. Okay, get as many done as you can here. All right, let's look at the first 2 here, guys. So our first one is calcium sulfate. So since it's written in words, I probably need to put it in its formula form so I can kind of find everything easily. So here's another example of why it's important to be able to do that. Okay, 2 plus, 2 minus. So I'm looking at calcium sulfate. So here's sulfate. Says it's soluble with most things, but the first thing I see in the not soluble row is calcium. So is this soluble or not? Not soluble. Okay, so that gets an NS beside it. All right, we already did potassium hydroxide because I didn't look up here to see if it's there. Soluble or not? Soluble, yeah, because potassium, like hydroxide's right here, potassium's in group 1. All right, so that's soluble. How many people have done number 3? Okay, let's look at 3. Lead 2 chloride. Okay, so that's Pb. That's the 2 plus kind, so that'll be PbCl2. All right, so chlorine's right here, soluble with most things, but I do see lead 2 plus is down in the lower row. So this is not soluble. What if it was lead 4? Yes. Okay, lead 4 plus isn't listed down there. Lead 4 plus is also incredibly uncommon, but okay, according to this chart, it would be soluble with lead 4 plus. Okay, keep going. I'll give you a couple more minutes and we'll do a couple more. All right, let's look at 4 and 5 here. So for 4, we've got tin 4 fluoride, so that's going to be SN, and it's with fluorine, so SNF4. All right, fluorine has its own column right there. Soluble with most things. I see strontium in here. I don't see tin in the lower row. Soluble or not? Soluble. Okay. And then copper 2 sulfate, CuSO4. Okay, so I find sulfate. It's right here. Soluble with most things. I don't see copper in the lower row, so this is soluble. Is this one of the things from your lab?
Yeah.
Yeah. And copper 2 sulfate was one of the materials listed. So one of your compounds yesterday was copper 2 sulfate. Spoiler alert, it would have dissolved in water, apparently, according to this. Okay. All right, how many people have done number 6? Okay, let's have a quick look at 6 here. So we got potassium bromide. Okay, bromine is right here, soluble with most things. Potassium's not in the lower row. Soluble. Okay, give you one more minute to get the last 2 done, then we'll go over those. Okay. Silver with fluoride. So silver fluoride, we got fluorine right here. Okay, soluble with most. Silver's not down there, so this is soluble. Okay, and then beryllium nitrate. Okay, just so you know, most nitrates are soluble. Whatever it is about nitrate, just about everything that has nitrate in it is soluble. That's why when you see nitrate right here, it says most underneath, and then there's only these very odd things that I have never ever seen or heard of, okay, other than this chart, that it's not soluble with. Okay, so beryllium nitrate is soluble. Questions on how that works? Pretty straightforward. You have 4 of those on your quiz tomorrow. Okay, I'll ask you 4 compounds, soluble or not, on tomorrow's quiz. Okay, I'm going to give you guys about a 5-minute break here in the classroom, and then we will move on to polar nature of water. All right, the second part of this lesson is about the polar nature of water. Okay. Water's a polar molecule, which means that the electrons aren't shared equally between hydrogen and oxygen. And this happens a lot in molecular compounds. And it has to do with a physical property of each element that we haven't talked about yet. On your periodic table, every element has a number written right above its symbol. Okay, so for lithium, that number is 1.0. For hydrogen, it's 2.2. That number is their electronegativity. It describes how tightly they will hold on to electrons. Okay, so you can see that a lot of metals have very low electronegativities. That's why they form ionic compounds. They're like, yeah, get rid of it. It's a hot potato. Take it from me. Okay? And they're happy to be rid of them. Nonmetals, on the other hand, typically have quite a bit higher numbers. Okay? Like, for example, fluorine is extremely electronegative, 4.0. Okay? That's way higher than the metals on the other side. Right? But you can see that there's kind of a varying degree here in the nonmetals of electronegativities. So if these compounds these elements get into a compound together, how close their numbers are is going to determine who gets the electrons more in the sharing of the electrons. So if we look at oxygen, okay, oxygen's got an electronegativity of 3.4, which is quite a bit higher than hydrogen's, which is 2.2. Now, that's pretty high for a metal. That's why hydrogen can be both a metal and a nonmetal. Its electronegativity is kind of right in the middle. Okay? And part of that is because a hydrogen atom is pretty simple. It's one proton and one electron. Yeah. If we calculate, we do the calculation here, right? 1.01 minus 1 says there's no neutrons in this. Unless it's heavy or deuterium. Okay, then it would have a neutron in it. Okay, which is an isotope of it. Okay, so hydrogen's got a lower electronegativity than oxygen. So what that means, tell your friend to go away. All right, so what that means is the electrons hang out around the oxygen a lot more than they do around the hydrogen. This diagram makes it look like, oh, everything's hunky-dory, we share it equally. But it's not. It's actually more like this. This is hydrogen's electron right here, and it really does this. Okay, it spends almost no time near hydrogen. Okay, same with this one. Okay, so they kind of move around like that. Since they don't end up on the top ever, what is exposed at the top of a water molecule? Hydrogen. The nucleus of a hydrogen atom, which contains what? One proton, the most positively charged thing that there is. So that means that the top of a water molecule is positively charged because there's these protons that are just up there. Okay? And there's no electron that's going around them because the electron hangs out down here because oxygen holds them more tightly. Okay? So what that ends up doing is creating two positive charges at the top of the molecule and two negative charges at the bottom, making it have positive and negative poles, just like the Earth has a north and a south pole. Okay? If we have vast differences between one end and the other, then we say something is polar. Okay? So in this case, this is a polar molecule because it's got a positive end, or ends, and a negative end, or ends, okay, as the case may be. Everybody okay with that idea? Okay? That's what creates a polar molecule, the unequal sharing of electrons creating charged ends. Okay? Water looks like this, but ammonia, okay, which would have like a nitrogen atom in the middle, has 3 hydrogen atoms. Okay? And so what ends up happening is you get like 3 positives and 1 big negative at the other end, okay? And it ends up being positively charged as well. So they kind of do this. Okay? They kind of go around. They're a little more evenly spaced than that, but it's squished and they're on the bottom and the negative's on the top. Okay? So they all look a little different, but what they have in common is there's negatives and there's positives, okay? And they're far apart. Right? Okay. Questions on that idea of polar. I'm going to have some stuff here that I'll have you copy down that's kind of like definition stuff. Okay, so in a polar molecule, let's actually just kind of change this and say in a polar molecule, sharing of electrons, all right, is not always equal, okay? Some elements are more electronegative than others, okay, and thus attract the shared electrons more than other elements, okay? So let's have you write those sentences, and then you can just write that that is called a polar covalent bond. Okay, I'll give you a minute to write that. Okay, so the bond between hydrogen and oxygen is a polar covalent bond. They're sharing the electrons. That can lead to another kind of bonding called hydrogen bonding. That happens between polar molecules. So it's not a chemical reaction. We're not actually changing chemically the material, but these materials bond to each other and essentially stick to each other. Okay? So a hydrogen bond happens with a polar molecule when its negative end is attracted to the positive end of the other polar molecule. Now, that other positive end is going to be hydrogen. Okay? Hydrogen is obviously always involved in a hydrogen bond. Okay? So it'll be between hydrogen and whatever the other molecule's negative end is. Okay? So in this case here with water, okay, the hydrogen bond occurs between a hydrogen molecule and an oxygen molecule. Now, if we look at a water molecule, it's got 4 positions where a hydrogen bond can occur. Because this is negative, this is negative, this is positive, and this is positive. Anywhere where there's a charge, a hydrogen bond can occur. Okay? Hydrogen bonds are very weak. Okay? They break, they reform easily, they break, they reform easily, but they're there. Again, they're not something that causes a chemical reaction. These things are not permanently stuck together like in a covalent bond. Okay? But they can create some strange behaviors. Have you ever noticed that you can actually overfill a glass of water? Right? And you get that surface tension on the top, right? It's called a meniscus. That is because water is hydrogen bonded to itself. Okay? It's a process we call cohesion. Okay? Sticking to yourself, cohesion. Okay? Adhesion means to stick to something else, right? So that's why glue and tape are adhesives. They stick unlike things together. Okay? Cohesion means like things are sticking together. Water is sticking to water with a hydrogen bond. How easy is it to break that surface tension? Easy. Touch it, it's gone. Okay? Apparently you could make a paper clip sit on it and a picture of it. I tried it for like an afternoon and it didn't work. Okay? It was time not well spent. But if you have lots of time on your hands and you'd like to try it, go right ahead. Apparently you can do it. So surface tension, not super strong because hydrogen bonds aren't super strong, but they are a link, okay, between polar molecules. This doesn't happen in materials that are not polar. You couldn't take like a glass of ethyl alcohol. You couldn't overfill it because ethyl alcohol, even though it's a clear liquid, okay, was one of our unknowns yesterday, okay, is not a polar molecule. It'll get to the top and that's it. Okay, it'll start spilling over, it won't make a meniscus. Everybody with me there? Okay. This is also why, how many people have used a graduated cylinder in the lab before? Okay, or a test tube or things like that. Okay. If you put a liquid in a tube, if you put water in a tube, it sticks to the side of the tube, right? And it makes a dip like that. Okay. That's because it's polar. It's making a hydrogen bond with the glass. Okay? Glass is a polar molecule. Water can stick to it by adhesion. Okay? You've probably seen this if you've ever poured a really, really cold drink, okay, and put it up on a humid day. You start to see the condensation on the outside, and some of those beads can get pretty big before they run down the side of the glass. It's because the water is making a hydrogen bond with the glass and sticking to it. Okay? Until it gets too big for those hydrogen bonds to be strong enough to hold it, and then it falls. Okay, making some sense? All right. So we need to know kind of what a hydrogen bond is, and we'll talk about that here going forward. Okay, so water molecules are about a right angle. The hydrogen atoms are about 90 degrees apart, okay? And that creates what we were talking about a minute ago, 4 bonding points on the water molecule for hydrogen bonds to occur. Okay? All right. Now, there's going to be a part of this that I want you to copy. I'm going to underline it right now, and I'll have you guys copy it down, and then we'll talk about it. Okay, so just that underlining. Okay, so you've probably all noticed this, okay? You've probably all at some point in your life accidentally frozen like a bottle of water, okay? If they're in a plastic container like this, that's not too much of a problem, right? Like what happens? Yeah, it expands, right? The bottom is no longer flat, usually falls over in the freezer or fridge or wherever you froze it, okay? But there's usually enough room in a plastic bottle for that expansion to occur without breaking the bottle. Back in the day when everything came in glass bottles, that was a much bigger deal, okay? There's no room for expansion in a glass bottle. It expands, it breaks the bottle, it shatters everywhere, okay? And then usually at that time, not all of it is perfectly frozen and you've got a giant mess, including broken glass somewhere, right? But when they freeze, this actually happened in my fridge the other day, okay? This canned Red Bull froze. Okay? They build these, okay, the cans and the plastic bottles now with room to tolerate that expansion. It's pretty rare that you would get a can of something to freeze and it would actually rupture out through the hole at the top. It can happen, but it's pretty rare. They usually have enough of an expansion area down here to tolerate that. Okay? But it's a lot of force, right? Okay, I mean, it's enough to change the shape. It's pretty hard to change that shape back. Okay, with your bare hands, you can sort of do it, but right? To think that water can just do that because it changes state. Why does water expand when it changes state? Because that's weird. Most things contract when they get colder. But water gets bigger. Okay? Well, that's not entirely true. Water will, as a liquid, will actually contract until it gets to about 4 degrees Celsius. That's where liquid water has the least volume. If you get colder than 4 degrees Celsius, what you're trying to do is push the water molecules closer together. Well, they have charged ends. If you start pushing them really close together, the negative charges and the positive charges, like the positives are getting too close to the positives, the negatives are getting too close together, and it's like pushing on a spring, right? You keep pushing, and then you get tired, and the spring goes back out. Okay? That's what happens with water. Okay? You get to a certain temperature, and those hydrogen bonds will not let you get any closer. In fact, they'll push back. Okay? And then water will get bigger and freeze. Now, once water freezes, it goes back to, as it gets colder, it contracts. Water will take up, the ice will take up less space the colder it gets. That's why if you're like on a lake, for example, and it gets really cold, you can hear the ice cracking. Okay? It's because it is actually contracting a little bit all the time. As it gets colder, and if it expands, it'll crack a little bit more. Okay? But this means then that an ice cube, solid ice, or solid water, sorry, floats on its liquid counterpart. Is that true for most things? If I had a chunk of solid mercury and I dropped it into liquid mercury, it would sink to the bottom. Okay? Almost all things are more dense in their solid state than they are in their liquid state. Water is not. Is that pretty important for living things? Okay? Ice floats on top of water. If it didn't, lakes would freeze not from the top, but from the bottom, which means they would freeze all the way to the bottom. Okay? And no aquatic organisms would be able to survive winter because there wouldn't be a nice layer of lighter ice floating on top, insulating the water from the really cold air above. Okay? It's a super important property of water that allows life to persist even though the air temperature is colder than the freezing point of water. Okay? Everybody okay with that idea? Okay. So, hydrogen bonds, okay, this here, the hydrogen bonds between water molecules, okay, so Whoa, that's not what I wanted. Okay, so let's just do this. Let's go water to water, okay, is called cohesion. Okay? Water to another substance is called adhesion. Okay, that's what's in this picture here. Okay, there we see water hydrogen bonded to nitrogen trihydride. So that's the adhesion. Okay. Both of those properties, adhesion and cohesion, are important. They both result in hydrogen bonds, okay, and they're both important for living things to survive. We're going to talk a bit about them in a minute, okay, but definitely you need to know those two terms. I guarantee they'll be on your quiz tomorrow, okay. They both involve hydrogen bonds between polar molecules. Adhesion, hydrogen bonds between things that are not the same. Cohesion, between things that are the same, usually water to water. Okay, so when water does this, it turns into a solid, but that solid is crystalline. Okay, ever heard the expression, there's no two snowflakes alike? It's not true. Okay? But there are a lot of different shapes for snowflakes to come in, and that's because of that polar nature. When they go out, there's any number of different crystalline combinations or fractal combinations that they could form as a result of that. Okay? That's why you hear that expression. Yeah, you could have a whole bunch of snowflakes in your hand and no two of them would be exactly the same. Okay? Somewhere in the history of time, I'm sure there have been, two snowflakes with exactly the same shape. Okay? But that's because of this crystalline shape, okay, and this polar nature of water. All right, this idea here, the tree transport or plant transport of water, this is going to come up a whole bunch. Polar nature of water is going to come up in 3 units in this course. Okay? We're talking about it here in chemistry from a chemical and physical properties perspective. Water's polar, it's not sharing its electrons equally. That can result in cohesion and adhesion. This is how plants transport water. If water wasn't polar, plants wouldn't be able to move it. Right? Believe it or not, even like a giant sequoia that's a couple of 100 meters tall uses 0 energy to transport water from its roots to its leaves. Okay? If you or I tried to lift the amount of water one of those things lifts in an hour, okay, from, for a couple of 100 meters, would it be hard work? Yeah. Yeah, we would have to carry it. It's a bunch of weight. Okay, we're moving it up. But a plant expends no energy to do it. And it does it using 2 things. Osmosis, which we'll talk about in the biology unit, and the polar nature of water. So, you guys have ever taken a straw, put your thumb over the top, or put it in liquid, put your thumb over the top, pull it out, and the liquid stays inside? Okay, that's because water is polar. What you're seeing there is both adhesion and cohesion. Hydrogen bonds are being formed between the water in the straw and the water in the water. Now, that only works for straws of a certain size. Okay? Most straws you would buy are going to be small enough that that'll work. But if I took a pipe, that was this big around, put it in water, put my hand over the top and sealed it and then lifted it up, would that work? No. Okay? Hydrogen bonds aren't strong enough to support a ton of weight. Okay? They can work for the straw. They can work for the little tiny microscopic tubes that help transport water up a tree. There's millions of them. Okay? They're only a few microns across. That's why it works. Okay? But I couldn't do that with a big pipe, because if I did this, the hydrogen bonds are trying to support a column of water that's really big and really heavy. And they can't do that. But a column of water that's only a few microns across, but is 200 meters tall, isn't very heavy. And the hydrogen bonds can hold it. Okay? So if we could see water molecules inside of the tree, this is what we would see them doing. We would see them hydrogen bonding to the cell walls on the inside of what are called the xylem tubes, okay? Because that's not water. Water is bonding to that, that's adhesion, okay? So we would see that. And we would also see cohesion. Water molecule to water molecule. How many people played with like a barrel of monkeys when they were a kid? Right? The little plastic monkeys, you could hook the arms together, okay? And some people are looking at me strangely. It might be a generation gap question these days, but okay, you used to be able to buy these plastic barrels full of little plastic monkeys, and their arms were like this, okay? And you could hook them together, and you could lift up the whole bunch of them by only pulling on the top one. Almost like a chain, right? They would hook together like that. That's what's going on inside the xylem for a tree with the water molecules. Okay? They're hooked together by hydrogen bonds, which are like the hooks on the barrel of monkeys. Okay? And I can pull on the top one, and that'll pull all the water up the xylem tube, because they're all connected. Okay? So all that happens is a water molecule evaporates out what's called the stomate. We'll talk about that in biology. Okay? It evaporates, turns into a gas. As it's turning into a gas and leaving the stomate, it's pulling on the liquid water behind it, okay? Lifting the entire column up. Okay? Now, there's also osmosis in there, which again we'll talk about, but it's the polar nature of water that keeps it together. If water wasn't polar, that wouldn't work. Okay? So, got to know cohesion. Okay? Cohesion, okay, as we said, is water to water. Okay? H2O to H2O. Okay, hydrogen bond. That creates surface tension, okay, things like that. Okay, and if you look in the notes package, that diagram is in there. As I said, you're going to see that diagram in 3 different units in this course. Okay, so it is an important diagram. It's one of those kind of processes you need to remember. Okay, plants use this hydrogen bonding, this polar nature of water. Okay, and then adhesion, okay, like clinging of a substance to another. Okay, so that's unlike things. Okay, that's a hydrogen bond as well. Okay, so you got cohesion here on the left. You got adhesion there on the right. Okay, you've probably all seen water beading, okay, and sitting on the surface of a leaf. Okay, leaves are covered in a waxy cuticle. This is a polar molecule, and so the water can hydrogen bond to it, but they'll only stay there until they get so big, just like the ones on the side of a glass, okay, or on the hood of a car. Okay, if someone has recently waxed their car, okay, the water will bead and it will sit on the top. Okay, that's actually what you want to see if you like your car's paint to stay good. You want to wax it, because if you don't, the water can penetrate the paint, okay? And then it can degrade it. The car can start to rust and fade and things like that. Okay, you put a waxy layer on it, you're letting it sit on top and hydrogen bond to it instead of penetrating it. Okay, making sense there? All right, so we talked about how plants use this. Are there any animals that use this?
Animals with like coats to protect them from getting like soaking wet.
Yeah, okay, anything that's got like an oily coat, okay, like a seal, okay, or birds, their feathers, okay, they repel the water, right? Like if you ever get something that's downy, okay, like a down-filled jacket or a down-filled sleeping bag, okay, even if they're wet, they can still insulate you because the water will not like penetrate and ruin their insulative capacity, okay? Aquatic insects, okay, have you ever seen like bugs that land on the water? Okay, they're doing the same thing. They're spreading their weight out so that they don't break that surface tension film, okay, and they can just sit on the water. Now, if something comes along and touches the water beside them, down they'll go because now the surface tension is broken, okay? Or the Jesus lizard, okay? They can walk on water, apparently, okay? All they do, they've got really splayed feet, okay? So again, it spreads and they move really fast so they can push on that water. Yeah, they're gonna break the surface tension, but not quick enough to fall in. Now, That's pretty good if they're going across fairly still water. It wouldn't work across like broken water, like a river or something. That'd be a lot harder because the surface tension's always being broken. Okay, but they can do that to escape a bigger predator and get across a a small body of water that way. Right, but all of that relies on the polar nature of water, surface tension, okay, things like that. Okay, questions on that? Okay, so tomorrow's quiz, naming, okay, properties of compounds. So like we talked about the solubility stuff there, and we talked about, so that'll be on there using the solubility chart. Be able to answer a question like, I have a blue crystalline solid that dissolves easily in water. Okay, what might this be, or what metal would this contain, or something like that. Those are the kind of questions from lesson 4 on physical properties. Okay, and then using the solubility chart, knowing the terms here, okay, and then obviously still naming from before. That's what's going to be on there tomorrow. Okay. All right, I'm going to put a couple of naming questions up here. I want you guys to just quickly do these to review. All right, let's have a look at the first 5 here. First one, ionic or molecular? Ionic, okay. So Be is beryllium, and it's with nitrogen, so beryllium nitride. Okay. Do I need any Roman numerals or prefixes or anything? No. Okay. Second one, S4O5, both non-metals, so molecular. Okay. What prefix goes on the sulfur? Tetra, sulfur, and whoop, that's a U. Okay. Sulfur, and what goes on the oxygen? Okay, pentaoxide. Next one, ionic or molecular? Ionic. Okay, so this will be lithium sulfate. Okay, how about the next one? Ionic or molecular? Okay, what would we call it? Did we forget anything? I hear lead sulfide a lot, but lead 2, right? Okay, guys, this is exactly what can happen on a quiz, right? I put one like this on here. You've done a few already that didn't need any Roman numerals, and it's really easy, especially if you're not looking at your periodic table, to forget. Okay, so I did that kind of on purpose. Make sure you're always checking for ionic compounds. Okay, this is lead 2 sulfide. Okay, and the last one. Copper to nitrate. Okay. How many people have done the next 4? Okay. All right, sodium sulfide, ionic or molecular? Okay, so I write sodium, it's a +1, sulfur, it's a -2, I drop and swap, Na2S. Okay, disulfur trinitride, ionic or molecular? Molecular, okay, how many sulfur? How many nitrogen? Okay. Potassium carbonate, ionic or molecular? Okay, so potassium plus 1, carbonate, CO3, it's a -2. Stop and swap. Okay, I could enclose the carbonate in brackets if I wanted, as long as I don't put a number outside. Okay, and last one, nickel 2 nitrate. So Ni, what does the Roman numeral tell me? Use the +2. Okay, and it's with nitrate, that's NO3, and that's a -1. Drop and swap, okay, so the 2 goes here, 1 goes there. Am I missing anything? Where does the 2 go, inside or outside? Okay, good. You guys should do fine on that part. All right, still have a few minutes left. I would suggest maybe checking with your group mates and see if anybody figured out a few more of those unknowns last night. Maybe see if you can put your heads together on any of those. Okay, good job today, guys.